Okay, so yeah, we'll just basically walk through and review the exam. And in the latter stages, we'll talk about some of the issues that you've probably run into when you were trying to analyze the driver decision data when they encountered a yellow light. Basically, it's signals changing from green to yellow to red. And so before we get to that, though, just real quick recap. There were a few fine details with respect to some of these definitions. I just wanted to make sure we're clear to everyone. And so I guess the plan at this point is to walk through these, and I would appreciate it if you would be so kind as to turn your cameras on so we can try to make this as interactive as possible. So I guess with that being said, Jordan, since you were brave enough to turn your camera on first, I guess I'll go to you. Can you give me a definition for what a null hypothesis is?
It is an idealized hypothesis that proposes no relationship between samples or a sample and a reference.
Okay, that sounds very similar. So I suspect you might have been taking that off of your exam even. So yeah, one key point of clarification when we talk about a hypothesis is basically a statement, right? And a statement that explicitly describes parameters were the key elements that I was looking for in that definition. And specifically, we're assuming generally that those parameters have no effect, or there's no difference between the populations that are being compared, or the factor that we're trying to determine whether or not it has an influence. And so there's a bunch of different ways people could articulate that. And so I generally give full credit across the board there. But the key point there, again, is that those hypotheses are statements about parameters. We're generally assuming that those parameters either aren't different from some reference value, or that there's no effect associated with that parameter as it relates to our specific problem of interest. Okay, and so continuing on there, the alternate hypothesis is basically a similar statement about parameters, but this one generally indicating that there's some difference or some effect or some meaningful relationship. And so that would run counter to the null hypothesis, and we could assume that those parameters are not equal to one another, that one's greater than the other, less than the other, whatever the case may be. Okay. So by and large, I think everybody had a pretty good handle on that. The only point that came up a few times was just the focus on the parameters. Okay. Significance level. How about Jesse? Can you tell me what significance level means? Or I will come back to Jesse momentarily. John K.
Yeah, it's the probability of rejecting the null hypothesis when it's true.
Yep, exactly. Or we could say it's the probability of committing a type 1 error. And so that's pretty straightforward. I think everybody across the board did really well on that one. And then a related term would be critical value. Travis, what's a critical value?
I said it's the point on the test statistic based on significance level and degrees of freedom to which the calculated test statistic must surpass in order to reject the null hypothesis.
Okay, yeah, so that's very, very good. The one point I would note there is, so that's a value from the probability distribution of that test statistic. So from the distribution of that test statistic, that would correspond to whatever that significance level alpha is that you had alluded to. And so that basically establishes at some pre-specified significance level or probability of type 1 error, how extreme of a value we would need to observe. So how much larger or smaller than 0, depending upon whether that's a one-sided or two-sided test. And if we're at or beyond that point, that would give us sufficient grounds to then reject the null hypothesis. So again, everyone seemed to do a reasonably good job on that one. P-value is a term that's related to each of the preceding. I would say there's a little bit more ambiguity with this one. So, Farish, can you give me a definition for p-value?
The probability that the data would have occurred under null hypothesis.
Yes, really close there. So it's basically, it's the probability that we would observe the specific test statistic from our sample conditioned on the fact that the null hypothesis is true, right? And so I think that the point that was least clear as I was reading through the responses to the exam was just conditioning that on the null being true. So it's not the, and we had a discussion, I guess it was last week or the week prior, about p-values and what they mean. So it's not the probability of us observing that sample per se, but it's the probability of us observing that value of the test statistic under the caveat that the null hypothesis is true, okay, which it may not be, and hence we can compare that directly to our significance level. And as that p-value is lower than the significance level, we'd come to the same conclusion if our test statistic was greater than the critical value, as we talked about previously. Okay. The acceptance and rejection regions for the distribution of those test statistics. Can somebody give me a definition for, I guess, either or both of those? They're obviously closely related terms. How about Folarin?
Okay, the acceptance region is the boundary in the test distribution that we can reject the null. That we cannot reject the null. Sorry. And then the rejection region is the boundary in the test distribution that we can reject the null.
Right. So both of those are characterizing specific areas of the distribution of the test statistic that we're working with. And so you stated that well. So the acceptance region is the area over which we're unable to reject the null. So basically that suggests that our data are compatible or consistent with our null hypothesis, or that's a range of values that would be very likely to occur if in fact the null is true, whereas the rejection region there will characterize the extreme values, the far tails of that test statistic distribution, and those values are generally incompatible with the null, and so they'd be associated with relatively large values, at least absolute values of that test statistic, which would support rejection of the null in favor of the alternative hypothesis. The issues I saw come up here most frequently were, for example, that the acceptance region constituted acceptance of the null hypothesis. And so just as a reminder there, we're generally not accepting the null hypothesis per se, and we're getting very much into semantics here to a large degree, but we're failing to reject the null. Now, there's a lot of nuance there, obviously, and so when you're writing out technical results, if that is, for example, if your t statistic's very close to 0, then I would probably push back less against failing to reject the null. I'm just saying you're accepting the null, versus if you had a value that was, say, at 1.94 or 1.95 on a two-sided test. So in that case, I would push back very hard if you're saying you're accepting the null in that case, because we're very close to the critical value in that instance. But again, by and large, I think everybody had a pretty good handle on this. The last three terms are also closely related to one another. So type 1 error, Asan, can you give me a definition for type 1 error?
Yes, it is rejecting the null hypothesis when it is true.
Exactly. And how about a type 2 error?
It is failing to reject the null hypothesis when it is false.
Exactly. Do you want to make it 3 for 3 and give me a definition for statistical power as well?
Yeah. It is the power of a statistical test. 1 minus beta is the probability of rejecting the null hypothesis when the alternative one is true.
Right. So basically, we're correctly rejecting the null in that case, whereas we're incorrectly rejecting the null in the case of a type 1 error, and then in a type 2 error, we're failing to reject when in fact we should. Okay. Does anybody have questions on any of these fundamental concepts? Again, I think by and large, everyone got somewhere between 16 and 20 points on this, and out of 20. So I think that went very well, generally speaking. So barring any questions, the next series of questions dealt with us working through some tests of sample means, essentially. And so let me try something here. This is either going to go very well or very poorly. And so, oh, I need to stop this share first of all. Okay, you can see the whiteboard now. So that didn't go nearly as well as I had hoped there. Let me, well, the text tool isn't as functional as I had hoped it would be. Okay, we're gonna, pull it back in. So the F-test is the simplest of these. So the first thing we're asked to do, so we're given basically telecommuting data before and after the onset of the pandemic. And so as you would expect, we found that, and we'll get to this subsequently, if we look before, during, and after the pandemic as to how many people were working from home, you'll see here these numbers went up between those before and after periods. It was even more pronounced during the actual height of the pandemic here. And so the first question we asked, and this was asked for two reasons, first of which is demonstrate that you could conduct a test of variance, and then it also led into a decision for the second part of this problem. And so the F-test, as you recall, is just a simple ratio of variance. And so in this instance, we could take the variance of the before data divided by the variance of the after data, or vice versa. And so as an example, the variance of the first sample here was roughly 1562.5. So variance of the first sample is 1562.5. Variance of the second sample was 707.5. And then our F statistic was just the ratio of those two. So 1562.5 divided by 707.5 gives us 2.21. And then this next part was probably the most missed part of the exam. And unfortunately, or fortunately, as the case may be, I didn't deduct any points because I actually had a mistake in the sample exam. So I was kicking myself as I was grading those over the weekend. But in this case, when we're conducting a two-sample test of variances, is that a one-sided or a two-sided test? Anybody?
Two-sided.
Oh, what did you say, Nishal?
Two-sided.
Right, it's two-sided, right? Because it's arbitrary which way we set it up, whether it's the variance of sample 1 over sample 2 or vice versa. So we'd obviously want to reject if we're in either extreme of that distribution. And so as you recall, in the case of the F, we'd want to basically set that up so that our critical value then would be F 0.025. Unfortunately, in the sample exam, I had used the 0.05 value there. Our degrees of freedom are n-1 for the first sample and n-2 for the second sample, so 4 and 4 in this case. And then from there, we'll actually find that in this case, our critical value is 9.60, okay? Now, it didn't really make a big difference if you had used the 0.05, that value would have been 6 point something, I forget specifically. But in this case, obviously 2.21 is less than 9.60. Therefore, we fail to reject H naught. And so consequently, we don't have sufficient evidence to claim that the variances are significantly different between those two periods, okay? And so that basically then feeds into our next question, where we're trying to determine, using a t-test, whether there was a significant difference in the number of individuals working from home during those before and after periods. And so in this case, how do we use the results from that F-test to select the t-test that we're going to utilize here?
The student t-test.
Yeah, students t-test. And why are we making that decision, Babak? Was that Babak? Sorry, I don't know who that is. Okay.
No, Samuel. Because we assume that our variants are equal.
Right. So we're assuming our variances are equal, and consequently our test statistic is simply going to be x1 bar minus x2 bar. All over the square root of our pooled variance times 1 over n1 plus 1 over n2. And so in our case here, those respective quantities would have just been 200 minus 232, which are the samples for the before and after periods respectively, all over the square root of 1135, which in this case, you'll recall that pooled variance is just the weighted average of the variances from sample 1 and sample 2. And when the sample sizes are equal, that's just a straight line arithmetic average. So 1562.5 plus 707.5. And that whole quantity times 1/5 plus 1/5 for those corresponding sample sizes. And that t-statistic then is negative 1.50. The critical t in this case, would this be one-sided or two-sided? Anybody?
Two-sided?
Yeah, typically you'd set this up as a two-sided. Now, I would, and I did, if you provided sufficient explanation there, you would not assume, I guess, perhaps, that the number working from home would go down during the after period. So you could make an argument based on prior expectations there that we'd only be interested in that one tail of the distribution. But in most instances, we'd operate assuming a two-sided test unless we had some prior evidence that would suggest that direction of interest would only be in one direction versus the other, okay? And so in this case, that critical t, if we assume 0.05 for alpha, would again be t 0.025, and our degrees of freedom in this case under students test, does anybody recall what the degrees of freedom are for that test statistic?
Is it n1 plus n2 minus 2?
Yep. So you've got n minus 1 for each of the two samples. So in this case, it's 5 plus 5 minus 2, or 8 degrees of freedom. And then consequently, that gives us a value of plus or minus 2.31. And so obviously negative 1.50 is not less than negative 2.31. So we're in the acceptance region. So again, we fail to reject H naught in this case. Okay. And I think everybody did a really good job on that one, likewise on part C here. So if we assume those data are dependent or paired or correlated with one another, which would make sense in this case because we have a bunch of different zones, and you would expect those zones that had more people telecommuting beforehand would likely have more people telecommuting afterwards. And we do see that as the numbers increase across each of these J sites, they also tend to increase during the after period as well. And so in this case, if we look at those differences, you'll recall our test statistic here is just X sub D bar divided by S sub D over the square root of N. Really wishing that whiteboard tool had worked right now, but. And so in this case, when we compare those, the before and after periods, that average difference we found was actually negative 32. So we tended to see larger proportions or larger numbers working from home in the after period divided by our standard deviation. And again, that standard deviation would be of these differences. So we would take the before minus the after, so we'd have negative 65 here, negative 35, negative 20, and so forth and so on. And so 32 was the average difference there, and the standard deviation of those differences was 19.87. And we simply divide that 19.87 by the square root of the sample size here, where that sample size is what? I worded that very poorly. What is that sample size? What does N represent in this case?
The number of pairs.
Right, so it's the number of pairs in this case. So N is equal to N1 is equal to N2. And so in our instance, we had those 5 observations. And so T then is just equal to negative 3.60. Now, just qualitatively, that's much larger than the negative 1.5 we had calculated previously. And so what does that suggest to us? Anybody?
Does it suggest that the paired test is the more appropriate of the two?
Yeah, so what's basically happening there, and I guess this is the most important point when we think about the paired test. If we assume these data were independent as we were in the prior case, we're basically testing whether or not that pandemic has an effect in these telecommuting patterns, okay? And so if these are all independent from one another, the differences between this sample and this sample are reflective of whatever the effect of the pandemic are, plus random noise. And that random noise includes any and all other things that would actually influence those telecommuting patterns, as an example, okay? Now, in actuality, what we've found is that there are other factors that are unique to each of these zones that tend to have some of these zones demonstrate smaller or larger numbers of telecommuters, okay? And so if you think about that conceptually, what we're doing under the paired test is we're explicitly accounting for that by taking these differences, okay? And likewise, if there wasn't actual correlation, so if these were just randomly scattered, so we had 150 versus 220 and 175 versus 240 or whatever the case would be in that instance, we wouldn't gain anything by taking the differences in those cases, okay? But in this case, that correlation is quite strong. And for example, if you ran in just the correlation coefficient on this, you'd find that that statistic was relatively high. And as a consequence of that, what happens, your difference isn't going to vary at all, obviously, right? Regardless of how we set that up, it's really the standard deviation term. And so if there actually is correlation, what's going to tend to happen is that the standard deviation of those differences is going to tend to be really small relative to what the standard deviation of both of those samples are collectively, okay? And that's important because we are basically sacrificing some degrees of freedom here, since we're working with just the 5 differences rather than the 10 data points we would previously. And so that's reflected by our critical statistic in this case, which is going to be T 0.025 with how many degrees of freedom here? Anybody? Thank you. Hand signals are fine if you don't want to necessarily have to talk into the Zoom box. So 4 degrees of freedom, so just n minus 1 in this case. And so in that instance, we'll find that our critical value is plus or minus 2.78. And so negative 3.60 is less than negative 2.78. There we go. We reject the null. And we claim then that there is a difference between those samples and that the pandemic did have an impact. And then also, I was expecting you to indicate here that the dependent sample test was more appropriate in that case. Okay. All right, and then the last item here is the Mann-Whitney U, which of course is the non-parametric alternative. And so in this case, we basically went through and we ranked each of those observations. And so to make this a bit easier to follow, let's see how well this works. So the first observation, we had a 150 and that was the lowest ranked. And so I'm going to assign a 1 there. That same zone showed 215 telecommuters during the after period, and so that was the 5th ranked case. And we can go through similarly for each of these instances. And I'm just showing what the corresponding ranks are in parentheses immediately after these numbers. Okay, and so we have ranks with 1 being the smallest rank in ascending order here, and with the 275 being the largest rank. We calculate R. There were a few small issues with this. So all we're doing there is just summing. So 1 plus 2 plus 3 plus 7 plus 9 would give us 22 for the first sample, and we have a rank of 33 for the second sample. We would then calculate our U statistic, which is just going to be N1 times N2 plus N1 times N1 plus 1 over 2 minus R, and depending whether it's R1 or R2. We can calculate that statistic in both cases, and we'll find that U is going to be equal to either 18 or 7. And then from that, we know that this generally follows the standard normal distribution. Now, I did introduce the small caveat that this is particularly intended for larger samples. And so with only 5 samples, it's less powerful than we would see for the large sample equivalent, less robust. But for the sake of time, I wanted a nice, simple, straightforward way for you to calculate each of these. And so that expected value of U is going to be N1 times N2 over 2, which in our case is going to be 12.5 because both of those sample sizes are equal to 5. Sigma U is going to be equal to the square root of N1 times N2 times N1 plus N2 plus 1 divided by 12, and the square root of that whole thing gives us 4.78 for sigma. And so then Z is simply going to be equal to our U minus the expected value or mean of U divided by sigma of U. And so that gives us 1.15. And since we're assuming that's distributed as standard normal, our critical value is just going to be plus or minus 1.96. And so in this case, 1.15 is less than 1.96. Ergo, we fail to reject H0. Okay. And so we basically ran 3 different tests, and only one of those tests led us to reject in this case. In the case of the Mann-Whitney U, what we'll tend to see is it'll generally give us smaller values as the parametric alternatives, unless we see significant departures from normality. With samples this small, it's going to be very rare that you would see the Mann-Whitney give us a higher test statistic than any of the t-test alternatives. unless it was really non-normal. So if you had a few outlying observations among those 5 and very large variance, for example, then we would potentially see some difference. But generally speaking, we're going to see this type of trend, and those will converge nearer to one another as our sample sizes get larger. And this statistic will tend to be larger only when we see significant departures from normality. Okay. Sorry, it looks like I've got a couple messages. Okay, so yeah, R is just the sum of the ranks. So sorry about that. And that was a point, it's been a while since we talked about the non-parametric stuff. But I recall in that slide initially, I didn't have that spelled out on the slide. I did post the revised slides subsequently. So, but yeah, R is just the sum of the ranks, not the average ranks, to answer that question that just came in from the audience. Okay, any other questions on the second problem? Okay. Third problem, again, just straightforward analysis of variance. I won't make you watch me type in all the various formulas here to calculate our respective sums of squares here. But I will just quickly replicate the Excel table here. And so we'd have our treatment sum of squares. And can anybody remind me, how do we calculate the treatment sum of squares? What's that taking the differences of? It's taking the squared differences between this quantity or these quantities and this quantity. Apologies for the ambiguous setup there. Go ahead.
Group means and grand means.
Yeah, exactly. So we're taking the means of each of the individual groups and we're comparing those to the overall or grand mean. We're squaring that quantity and summing it. And in our case, that gives us a very large number, 271,413.33. The degrees of freedom for the treatment sum of squares, what's the formula we use for that quantity? Anybody? Comment?
It's number of groups minus 1.
Yep, it's the number of groups minus 1, or A minus 1 in our case. We have 3 groups, so 2 degrees of freedom. And then our mean squared is just going to be the ratio of that sum of squares divided by its associated degrees of freedom. So that's 135,706.67. And the error sum of squares, so this would be representing what? How would we calculate this quantity? It would be the squared difference between what values?
The individual observation and the group means.
Yeah, exactly. So this is taking each individual observation, subtracting off that observation's respective group mean, squaring that quantity, and then summing it across our sample. And so in our case, that would give us an error sum of squares of 15,330. Our degrees of freedom here are going to be capital N, which again, in our case, would be lowercase a times lowercase n, or we've got 3 groups, each of which has 5 observations. So that would give us 15 minus a, which is 3 in our case, 3 groups. And so we'd have 12 degrees of freedom. Our corresponding mean square for the error would be 1277.50. And then just for the sake of completeness, our total sum of squares, this would be each individual observation minus the overall or grand mean, that quantity squared and summed. And that would just be the sum of these 2 quantities, obviously. So 286,743.33 and 14 degrees of freedom. And so again, if we take this ratio here, that's just going to give us our sample variance back, right? Okay, and then our actual test statistic to determine whether or not those treatments had an effect, or in this case, whether the pandemic had an effect on telecommuting. 106.23, and so that's very large compared to the corresponding critical value. And so our p-value here is 2.34 times 10 to the minus 8. And so based on that, we will reject the null and claim that there is a difference in telecommuting patterns. That was poorly spelled due to the pandemic. Okay, and then from there, the next step was to calculate Fisher's LSD. And so in that case, the first thing we're doing is determining our critical T value, and that would just be T 0.025 with 12 degrees of freedom, so the same 12 here, so capital N minus A. And then we're multiplying that by the square root of 2 times our mean squared error divided by N. And so in this case, that T value is going to be 2.18 times the square root of 2 times that same MSE we see here, 1277.5, all divided by our sample size of 5. And so we end up with an LSD value of 49.25. And so all we would do from this point is compare each of those differences. So if we look at the before minus the during, we saw an increase of 300 in that case. If we look at before versus after, as shown in the preceding problem, we'd have a reduction of 32. And if we compare the during minus the after, we'd have an increase of 268 in that case. And so we'd make each of these pairwise comparisons against the 49.25. And so we would say, yes, significantly different. No, not significantly different. And yes, significantly. Okay, and so in effect, what that's saying basically is that our telecommuting rates were significantly higher over the course of the pandemic. And though we did see some differences between the before and after period, that increase in telecommuting was not significantly different, at least based upon this sample of 5 zones here. Okay. All right, and so any questions on the ANOVA?
I have a quick question. Why did you use the T value of 2.18? Is that for a right-tailed or a left-tailed?
So I guess this critical value right here, we're conducting this as a two-sided, first of all, okay? And then the corresponding degrees of freedom in this case, so that 12 is due to the fact that our mean squared error has 12 degrees of freedom associated with it, is where that's coming from. And so hopefully, I don't know if that's answered your question or if you had further questions.
I guess I was just wondering, because in the sample exam, like the corresponding T value that was used for the LSD was based on a two-tailed, and I guess I found a different value, so maybe we can talk about it later. But.
Oh shoot, no, because this is I bet I know what happened there, because I was also seeing some discrepancies on this problem. This is one of the things that delayed me in grading. Does anybody know how Excel gives you critical T values back? I didn't know until this weekend, and then I was very angry. So let me I'm going to very quickly share. Okay, so we can use the t-distribution function here to determine whether or not there's a significant difference. Okay, so as an example, if I type in 2.18, this might I don't know if this will make it more or less confusing. So if we type in that 2.18, that critical value, and we say that we've got 12 degrees of freedom and it's two-tailed. So that's basically corresponding to that 0.05 number we saw, right? And likewise, if I plugged in a value larger than that 2.18, like let's say 4, we're going to see a value that's significantly less than that, right? And if we continue, and it'd be helpful if I actually showed you what those numbers were, I guess, here. So T 2.18, 4. And so you can use this to calculate a t-statistic in Excel, and I think I've showed you folks this before. But in this, you specify whether it's one-sided or two-sided. Now, you can also use, and so that was just, that's for the equals t-dist command. There's also an equals t-inverse command. And so for that one, you can enter in your corresponding probability. So when I went through and put together the solutions for the sample exam, which apparently was another error in that sample, so I'll have to go back and double check the math on all of these. I entered 0.025 with 12 degrees of freedom. And so what this will give you back is the t-statistic that corresponds to that probability and that number of degrees of freedom. But if I hit enter here, you'll notice that's not giving me that 2.18 back, it's giving me 2.56, okay? And I didn't even check when I went through, I just plugged that back into the sample solutions. And so my apologies for that, but I will go back and give those points back to anyone. But we want to set that to 0.05 here, and that's where the 2.18 comes back. Now, I don't know why it's set up this way and they don't give you the flexibility, but Excel, when you use that t inverse, always gives you the two-sided at that level of alpha. So if you put in alpha 0.05, it's assuming two-sided. So if you're doing a one-sided, you basically you need to adjust that quantity accordingly. Okay. So does that make sense, Jordan? Then why there was a discrepancy? And so that was on my sample too. Then that's okay. So the mean exam score has just gone up marginally for whatever that's worth to everybody. So any other questions on the ANOVA, or I guess anything else we've talked about up to this point? Okay, so the bulk of what I want to talk about for the rest of the time, we're just going to basically play around with the data sets that we had started introducing. So let me just quickly share. Oh, timeout. There's another. I was not aware of this function. So hold on, I'm going to share back. So equal t inverse 2t, is that right? So Farish has just informed me t inverse. Sure enough, look at that. So 0. Interesting. Okay. So there is a command that I was unaware of, but thanks Farish for that. So by default, again, you can see here that this is giving you the corresponding value for alpha, and if you wanted the alpha over 2, then you would use a corresponding command there. So thank you very much for that. And now I'll pull it back in to remote desktop. Okay, and so I've got the data set here. Now I saw significant variability in how this problem was approached, specifically with model building and assessment of some of the underlying assumptions. And I've used this data set or some variant thereof a few different times in different contexts. And so this is the first time I've seen this much variability in terms of how people approached it. So I just kind of wanted to walk through things. So I guess from a big picture perspective, let's talk through what were some of the issues that you all ran into when we attempted to analyze this data set, or what concerns did you have as you were trying to build your models? Any thoughts? Or was it relatively straightforward and no issues and all your models were perfect, perhaps? Okay. Okay, we've got something in the chat. Okay, variable selection. Can anybody elaborate on how variable selection, any of the challenges you ran into there?
I had questions about using the yellow interval along with speed and the posted speed limit. It was kind of the first issue that I ran into.
Yeah, so there are a bunch of concerns, or what appear to be concerns, and every time I talk about endogeneity, I think we all get a little bit hypersensitive that there could be endogeneity everywhere and you've got kind of circular relationships. And I think that was John's concern. I recall going through your exam specifically there. But if you look at the yellow time is generally calculated based upon a formula from ITE that makes assumptions about speed and the distance the vehicles are traveling. And so clearly you'd expect relationships between these. And so I guess to try to demonstrate John's concern here, one thing I guess that we could do is if we, so I guess there's several different ways to approach this. Let's just, we'll just do a quick regression model. And so this was a frequent concern that came up, generally speaking, in selecting variables, is people express concerns about correlation. Now, correlation can be problematic, but for that to occur, the correlation has to be quite strong, generally speaking. And so as we think about this, so the variables that were of particular interest to John here, we said yellow time, and what were the other two, John, that you said were concerns there?
Both speed and speed limit, assuming speed and speed limit are related also.
Okay. And so if we think about this in concept, just going into this, irrespective of prior expectations, if that yellow time is larger, what do we think would happen to the likelihood of a driver stopping? Would they be more or less likely to stop with a longer yellow?
They would be more likely to stop.
They would be more likely to stop with a longer
If
yellow?
the yellow time is lower.
Okay, if the yellow time's lower, they would be more likely to stop. That's probably makes sense. So the thought here, and this isn't something that's consistently shown from site to site, but longer yellow times, you generally see that drivers are more likely to proceed through the intersection or not stop. Now, it's debatable what's actually causing that effect, because you could say, for example, that, okay, drivers realize they have more time, they have a longer yellow, and so they're going to go through as a consequence, which may be true, but I don't mean to give people too much credit. I don't think people are that smart or that observant. Maybe smart's not the right word, my apologies. But generally speaking, I don't think your typical traveler has a good sense as to how long yellows are, generally speaking. But what are the other things that might be happening here? I guess, John, back to your preceding point, when would we tend to see longer yellows?
sites with higher posted speed limit?
Yeah, so if the speed's higher, we need to provide drivers with a longer time to react, and so consequently, we make the yellow longer as a consequence. Likewise, if the speeds are higher, drivers, it's kind of a circular argument here, so I can see how you would have concerns. If the speeds are higher, drivers need a longer time to react, ergo, that's why we make the yellow longer, right? So that's how we get into kind of this cycle. Now, what we can do, I'm going to run some collinearity diagnostics when I get the model output right here, first of all. And so just looking at these values, so you may or may not recall when we talked about the variance inflation factors, this is just basically looking at how strongly these variables are correlated with one another. So we estimate a regression model for each of these individual predictors as a function of all the other predictors in the model. And so we just take 1 over 1 minus the corresponding R squared of that model. And so the general rule here is if these variance inflation factors are 5 or larger, that's when you'd start to have concerns, particularly if they're above 10. So just on the surface, there's not a particular concern here. Now, as we go through and build this model, and now granted, you didn't have an entire week, you just had the 1 day to work through this in addition to the other problems there. But you can also work through, as you add these variables one at a time, you'll want to see what happens to these parameter estimates. Do they change sign? Do we see significant differences in these values? And I guess to one of the initial points here, if we actually look at the relationship between, let's say, yellow time and speed limit, okay, so it looks like there might be something happening here. So generally speaking, we have longer yellow times for higher speed limits, but there's quite a bit of variability here from site to site is what we're seeing, okay? And so while there is correlation here, my general perception on this, having worked with the data set numerous times, is that correlation is not a particular problem here. But with that being said, there are some different ways we can try to work through some of these variables and look at the relationships in a slightly different manner. And so I guess to that end, what do you folks think the strongest predictors would be of this decision on the part of the driver? Okay, hold on, I got something in the chat. Oh, so timeout. I had a question that came up a few minutes ago. Wouldn't it be the case that drivers won't know how long the yellow time would be? Yeah. So generally speaking, I would agree that drivers would probably be unaware of that. Okay, so back to the question, what do you think the strongest determinants would be of that stop-go decision here?
The distance.
Yeah, so I would say distance is going to be a very strong factor there. And so we'll just start, let's do a quick scatter plot of, and this will reinforce a few different points here. So if we look at stop versus distance. Okay, so first of all, the nature of the data here are kind of different from any of the data sets we've worked with up to this point. And the reason for that is because Y only takes 2 values, right? So just from looking at this at first glance, it might not seem like there's a lot there necessarily, but if we put a best fit line through this, it's going to basically, it's clearly going to be a line that's increasing as we go left to right here, right? There's a much larger cluster of points over on this end and a much larger cluster of points over on this end. All other things being equal, the further you are from that intersection, when it changes to yellow, you're going to be more likely to stop, right? In addition to distance, is there anything else that would be a particularly strong determinant here?
Vehicle speed.
Yeah, so it's speed and distance would be the 2 big ones here. And so we'll look at speed likewise. And so stopping versus the speed at the time the signal changed. And then we're going to see a similar type of scenario here where if they're traveling at a very high speed, they're going to be much less likely to stop. So we see a cluster of points. It doesn't look as pronounced, but keep in mind there's a whole bunch of points laid on top of one another here, and we definitely would see a decreasing trend as we move left to right here. But now as we think about this, when you're fitting that best fit line through there, you'll notice it's not really fitting that data particularly well at all, basically here, right? And that's just given the fact that Y can only take these two prospective values. And so regardless of what variables we use, when we start looking at the residual plots, we'll see that some problems start to arise, okay? And so before we get too far into that, I think there was at least one other person, and again, I haven't got through all the exams yet, but so speed and distance clearly both have strong impacts. Is there a way we could synthesize that information and instead of working with those two predictors, work with just a single predictor that would quantify that?
We calculate time to stop?
Yeah, right. So the other way we could look at doing this is looking at the time to stop. So if you take the distance they're traveling divided by the corresponding speed, then we would have essentially the time that they would have to stop prior to reaching the intersection, basically, okay? And the interpretation there would be similar. You know, the longer time they have to stop, the more likely they are to stop. The less time they have to stop, the less likely they'd be to stop. And I will quickly show you a similar plot there. And again, it's very similar to what we had seen previously, but this is basically combining both that time and distance information. So we do see a little bit better separation than we had previously. And so, of course, if you have very limited time available to stop, you're going to be much less likely to stop. And so it's getting a bit cleaner than we had seen previously. Okay, so I don't know. I know there was at least one person who worked through that approach there, but that was actually, and I don't know how many of you would have come across the initial paper we had developed, but that was one of the key metrics we used for some of our initial analysis for this study, which now, gosh, was conducted probably 6-7 years ago, I think. But okay, now back to my initial point after all that rambling. So what we'll do at this point is, well, we'll go through these real quick. So speed limit, we think that would have an influence potentially. Yellow time, speed, distance. I guess we'll just throw everything in here. And normally I don't advocate for just throwing everything in, but the one thing I didn't throw in here was the count. And I don't know if, I know some of you looked at that in some form or fashion, but we did actually see some impacts of count here. Now that wouldn't necessarily tell us anything meaningful about the data. And actually, let's throw it in here and let's just see if it's significant. I can't recall if just at the onset that would be, okay. So the count variable does end up being significant here. But basically what's happening there is there was a small subset of sites. So these data were collected from 80 plus intersections all across the United States. And we combined data from several different studies. And so it just so happened that the data that were collected in Nebraska were collected at high-speed sites that had advanced warning flashers installed. And so consequently, what we found at those sites is since they had, and so these advanced warning flashers, basically, right as the signal's about to turn to yellow, they'll give an advance warning to drivers so that they have more information and are better prepared to stop in those instances, okay? And so what you see consistently is that the sites with the all-way flashers have significantly higher likelihood of stopping, and a very large positive coefficient here in this case. And so there's also a relationship though with the count because we don't have a balanced sample here. And this is something that happens frequently when you have sample, if you got some subset of your sample that is different in some inherent characteristic that you're not necessarily directly accounting for in the model, then it becomes problematic, and we have what we'll refer to as spurious correlation. So it looks like there's some effect here, like so sites that have larger numbers of vehicles. So you could think, well, does that mean that higher volume sites have greater concerns here, or what's actually driving that? And so in this case, we'd actually use different methods to collect the data at the subset of sites that had the all-way flashers. And so that's basically a carryover effect here. Okay, so without having knowledge of that, though, you'd obviously have no basis for making that assumption. And if you saw that variable, it should raise suspicions to you as to whether or not there's anything meaningful there. So I'm going to just very quickly rerun that and pull that variable. Okay. And so now as we look through this, we see that nearly every variable here is statistically significant the way this model has been parameterized. Now, yellow time is not, but depending upon how you specified your models, there are certain combinations where yellow time would make sense. And so when I was evaluating this, I was basically trying to follow everyone's thought process and their justification for how they structured the model. And so there were some cases where I give very high credit for, I don't know how to refer to them other than very poor models. And they're very poor models just in the sense that they're certainly not the best predictive models for the data set. But as those students walked me through their rationale and how they proceeded through the model selection, then it made a lot of sense. Okay. So as we go through these generally, we'll find that most of these results are probably consistent with our expectations going in. So at higher speed limits and vehicles that are traveling at higher speeds, we see that those are negative, and so people are significantly less likely to stop as those speeds increase. Now, obviously, there's going to be some correlation between speed and speed limit. Are there other ways that we could try to capture this? I don't recall whether anybody had done this, but I've played around with these data in a few different manners. So speed and speed limit, the relationship between those two, is there any way we can jointly make use of that information?
You could look at vehicles, like how much they were exceeding the speed limit, the difference between the speed and the speed limit.
Yeah, exactly. So that's one thing that we've looked at in the past. So if you take the speed minus the speed limit, that would help you to capture differences between drivers who tend to go very fast relative to other drivers, right? So if you got people who are tending to drive significantly above the speed limit, my hypothesis going into that, or my alternative hypothesis, I guess, going into that, is that those more aggressive drivers would also be more likely to run the red, as an example. Okay, so that's a way that we could try to tease that out. And that would also, to a degree, appease some of the concerns we'd have as to potential correlation. Okay. Anyway, it's just something, as we go through, these are a few of the general thoughts I just wanted to bring up, because I had spent a very long time working with this data set. And so I'm quite familiar with some of the effects that are underlying here. Yellow time, so we talked a little bit about that. As yellow time gets larger, we find that drivers are less likely to stop in that case. And again, we don't necessarily know what the reason is for that, whether it's some inherent behavior on the part of the driver, which I would be suspect of, or whether it's just some characteristic related to those sites that have the longer yellow times, as an example. Okay. Auto enforcement, this is a very strong one. So if we use cameras to automatically issue tickets and citations when drivers run a red light, that has been shown by various studies to have very strong effects. And so we do see significantly higher likelihood of drivers stopping in those situations. Similar to the yellow time, if we have an all red interval, and I know not everybody's necessarily an expert in traffic operations here. And so that's basically just the factor of safety that we build in so that the signal is red on all of the approaches to the intersection to allow red light running vehicles to clear out and minimize the chances that we'd have an angle collision at those sites. Okay. And so again, this one's a little tricky because do the drivers actually know that there's an all red phase, which oftentimes might just be 1 second in duration? I would suspect probably not. And so this is a variable that might be capturing some other things. Part of that again would relate to the speed and the distance of the intersection. So for wider intersections and higher speeds, we would have some concerns there that would alter the way we would select that all red interval. So just another thing to be mindful of. The advanced warning flashers again showed the strongest effect. And so this was a specific subset of roads that were high speed, had historical data that suggested red light running was a problem there. And so these were tested out and they showed very good performance. Now, I don't want to get too much into the weeds here because we've only got about 14 minutes left here. But one concern that arises there with the all-way flashers is that if you provide that advanced warning, drivers might start to stop too frequently, and you'll have this mix of drivers. And if people start like right when that light goes to yellow, it could increase the risk of rear end collisions, which is another factor that we had looked at a little bit here. But and back to the primary factor of point of interest here, that's what we're basically demonstrating here. And then the last couple, we see drivers are more likely to stop at intersections that have a greater width. And that probably makes sense, but that's also somewhat related to some of these other factors, including speed and the timing of the yellow interval, etc. And then we also see drivers are more likely to stop if there was a pedestrian signal. Okay. Any thoughts as to what that might be capturing? Anybody?
I was thinking like the red signals some of them might have countdown timers.
Yeah, and so actually, thanks, Falarin. That's a great point. And the data set I had initially, and I actually removed the countdown signal variable before I sent the data set out to you. We had done some evaluation of this. We actually found that the countdown itself didn't have a significant influence, but the PED signal did, and there's some weird selection bias going on there that I won't delve into because that'll create too big of a tangent here. But even if it's just a normal pedestrian signal, if it's not necessarily showing the countdown to when it's about to go from green to yellow to red, it's still providing you with the flashing red hand as an example. And so even that bit of information is giving drivers some advanced knowledge. So I think that could explain part of this. Now, again, we might be giving the drivers too much credit to some degree there as to being that perceptive as to what's happening with the PED signals. If it was all traffic engineers, I guess maybe that would be the case. But outside of that, if you think about where PED signals are installed, they would tend to be installed on more urbanized facilities where speeds may be lower. And so we're accounting for some of these effects, but inherently there's going to be some potential selection issues that just there are mechanisms that lead to pedestrian signals being installed or flashers being installed or yellow time policies that we're not necessarily explicitly capturing in our model. And so those are a few things you want to be somewhat cognizant of. Okay. Hold on, we got a few messages in the chat. Okay, what's the advantage of combining speed and distance into one variable, as was alluded to previously? So if you think about it in concept, you're basically, and it's kind of interesting. If we look at this, I'll just run these. I'll run these analyses. So if we just go time to stop, let's see, our adjusted R squared is 0.439, and I want to say these were nearly identical to one another. If we look at speed and distance, so in this case, adjusted R squared 0.438, and so that's providing Jesse some insight there. So it's not a huge difference, but we do find that using the one variable as compared to the two variables gives us at least an incremental improvement in R squared. Now our sample is so large in this case, we're not particularly concerned with losing that degree of freedom. But if you think about the interpretation of this, and the driver decision-making process, and this is, so the paper we had authored on this, and actually we've got a few papers focused primarily on time to stop. And the reason for that is because we were trying to conceptualize how are drivers making that decision, okay? So is the driver saying, okay, I'm 100 feet from the intersection, or I'm 200 feet from the intersection? Generally speaking, people aren't that good at guesstimating distances and relative locations, and likewise relative speeds. But if you look at it temporally, and that person is 1 second out or 2 seconds out, or a half second out, our feeling was that had better discriminatory power and a better empirical basis. Now, in this case, as you see in the model results, if you use those variables separately, you're going to get very similar results ultimately, but we do see some incremental improvements if we use that time variable. Okay. Oh, that's funny. So I hadn't read, there was a subsequent comment that asked that very question. Yeah, so we get similar results here, but we find if we combine them into just the time variable, there's a slight improvement in the model goodness of fit. Okay, and then beyond that, I think the other point I want to make sure we get to here before I keep rambling on and we run out of time is some of those underlying regression assumptions. So let's construct some plots here. And I'm going to save our predicted values and our residuals. And let's throw at least a few different variables in here. I know auto enforcement, auto flashers. We'll start with those. Okay, and I guess just as an aside, no concerns really with multicollinearity here. Those variance inflation factors are quite small. We come down here, we look at the histograms. Interestingly, so our dependent variables are just zeros and ones. But when we look at the residuals, that's fairly good, fairly close to normality. And I know a few people had raised concerns here. There are some departures here. I think generally speaking, it wasn't a particular concern to me, but we will circle back to this in our subsequent lecture. Now, the big issue that people ran into is when we started to look at these plots, though, of the residuals. And so if we look at our residuals versus our predicted values, okay, so it looks like we might have a tiny bit of a problem here, right? So what we would hope to see is basically a shotgun blast. These points are randomly scattered. And so when we're looking at these residual plots, we're basically looking at two different things. We're looking at whether there's any sort of trend or correlation, and then we're also looking at whether these variances are equal. So starting with the first, how about the variances? Do we have any concerns with the variances here? I would say we have absolutely zero concern with the variance, right? These are perfect homoscedastic, right? If we go to the independence, we have a major problem here, though, obviously, right? Because these are not a shotgun blast by any form or fashion. They're consistently, in this case, decreasing as our predicted values are getting larger here. And so the fundamental question then from our perspective is, well, why is this happening? Thoughts? So how are our residuals calculated? It's basically, it's y minus y hat, right? And what's true of our y's?
The problem is that the y is the probability 0 and 1. But the y that we calculate by the model is it doesn't have range. It is not categorical. It gives us values from minus values 0, 1, and values between 0 and 1, and even higher than 1. So because of that, the lines here in this figure are in this shape.
Right, exactly, right? So our actual observed values are just, they're going to be 0 or 1 in all cases. Either that person didn't stop or they did. And the results from our regression equation aren't bounded by 0 and 1. In an ideal world, they would range between 0 and 1. But what you'll notice here, there's a significant number of cases where we predict negative values for the probability of stopping, or values that are greater than 1, right? And so that introduces just some general concerns as to the practical usefulness of this model. Okay, now interestingly, as we'll start talking about in the next lecture, it turns out those problems aren't quite so bad as we may have feared initially. But one thing I wanted to do, so that's the big takeaway here, is that we've got major problems. You didn't really have enough information to be able to diagnose how severe those problems are. You'll be able to do that after we go through some logistic regression analyses subsequently. But I did want to very quickly just talk through a couple things in concept here. So first of all, okay, it's not letting me, let me go up to here. So if I estimate a model with just an intercept term, just a constant term, and pardon me, I took a shortcut here because I couldn't remember how to do a constant only model in the regression framework there. We find that values equal to 0.528. So what does that number mean? Anybody? So if our constant, if we estimate a constant only model and that intercept term is equal to 0.528, that means that
more vehicles stopping than not stopping.
Yeah, so basically 52.8% of our sample stopped is what that's telling us, right? And so as we start adding variables to that model, and so I guess in easy, straightforward way here, let's say we look at the auto enforcement. And so in this case, we'll find our constant term is 0.511 and our auto enforcement term is 0.129. And so what that says is sites that don't have auto enforcement, roughly 51.1% of drivers stop. Sites with auto enforcement, that increases to roughly 64%, right? And we can continue doing this. And as the reason I'm bringing this up is because it's important. Let's get rid of speed. Let's put distance in. Okay, now in this case, you'll notice that auto enforcement term is still relatively similar in magnitude. The constant term now doesn't really have any meaningful value to us. I would still strongly advise us to keep that in the model as we talked about previously. But this is basically saying for each additional foot the person is upstream of the intersection, we see a 0.3% increase in their likelihood of stopping. Okay, and so I just want to bring this up because we can interpret these things naturally, and so we could even get back to a natural value for like the constant term in a roundabout way. So if we assume some arbitrary value, like let's say a distance of 100 feet upstream, we could plug that in, and then with the constant term, we could say at a distance of 100 feet with or without auto enforcement, we could calculate what the probability is of that person stopping under those conditions, okay? Likewise with each of the other variables here. Now, when we look at those residual plots, one thing that came up, and I apologize, I'm 1 minute over time here, so I understand if you have to bail, but if we look at residuals versus, let's say, I think auto enforcement might have been one of the two. So interestingly, in this case, we had a few students who surmised, well, there doesn't appear to be a problem with auto enforcement or really with any of the binary variables as compared to what we saw previously with those lines that are consistently going up or down, as the case may be. Now, the reason we're not seeing that is because there's only two categories here. If there was a third or fourth category, so there actually is that same trend is being observed here, but there's just so many points stacked on top of one another. It's not as evident how big of a concern that trend in the residuals is, for example. And so I bring that up just because a few people had tried to work through and assess, so which of these variables, these predictors, didn't have problems associated with it in terms of the residuals. And the answer is they all had problems. And that's just simply due to the fact that our data only take two values. And so there's no way to work around that. There weren't really any good transformations we could do or anything of that nature. That's just an artifact of the data set, is that there are some inherent limitations when we try to apply ordinary least squares to binary variables, essentially. Okay. We'll discuss this issue in much greater detail on Wednesday when we start talking about logistic regression. But before doing that, does anybody have any last questions before we wrap up? Again, those exams should be graded and back to you by Wednesday. I'll need to double check that the issue we had with Fisher's LSD to make sure that I don't penalize for a mistake that I demonstrated, I guess, on the sample exam, unfortunately. So, and then do you guys want me to post this recording? It was a little sloppy on my end here, but if this would be valuable, happy to post it. So okay. All it takes is one. So I'll post this later today. And then on Wednesday, I'll also talk briefly about term paper. I would probably be good to set up some individual check-in meetings. It's been kind of clunky trying to do that as a large group. So maybe if we just, find 5 to 10 minutes to chat at mutually convenient times, or I can set up just like a dummy assignment just to check progress. But I just want to see where everybody's at in terms of pulling their data together. Because we've got, roughly a month or so left in the semester, which is still reasonably good time if we're able to pull that data set together in short order. But anyway, that's all I have for today. So I will see you all again on Wednesday, okay?